Alright, so we have position of ball rolling in a straight line is given by that equation, where x is in meters and t is in seconds. Determine the position of ball at t 1, 2, 3 seconds. Do I need to do part A? Just out of curiosity, I'm glad to, but just plug it in. Plug in those values for t. Who's with me on this one, just so I know who to kind of try to make eye contact with? Okay. Okay. What is the average velocity over the interval from t equals 1 second to t equals 3 seconds? Okay, so I'm going to do part B here. See if I can't work small. I'm going to remember that velocity is the derivative of the position. And so the derivative of 3.1 is 0. And then I have negative 4.6 plus 2t. Okay. And if I think about that, that's linear, right? That's a linear equation because there's no t squared. And so if it's linear and it's from 1 second to 3 seconds, isn't the average going to be at 2 seconds? I mean, maybe I'm just having Thursday brain. Let's see. This is that looks like that, right? Has a slope of 2, has a y-intercept of negative 4.6. Sorry, I should have probably labeled these V and T here. And so if I want to find the average, it's just going to be halfway between 1 and 2. And then the instantaneous, so that would be at 2 seconds. Oh, and then it wants me to find the instantaneous. Let's try that. So I wonder, so I'm thinking 2 times negative 0.6 and 1.4. I wonder if that's right. So
engines up and running. 2, 1, 6, 5. Three engines up and burning. 2, 1, 0.
all right. So function f of t of time t has a constant rate of u given by the derivative of f with respect to time. We're an expression for the change in the value of f, delta f, on the interval between t1 and t term in terms of u. Just seeing what the little icons mean. Okay. So we know that delta is always final minus initial, right? So we want to f of t1 on per terms of u. Interesting. Okay, I hit hint. It didn't give any, did it?
No, I think.
Where?
Notice that use a constant.
Oh, okay. Try any of the expressions for you, but make sure you set your limits carefully for the right result. Okay. Do I have a value? No. Okay. So is what it's saying is integrate u from Q1 to Q2 of Q2. Alright? And so,
Might be the integral df.
it would just be, this would just equal, yeah, which is just f. But it would be, yeah, that's where I was thinking it was just, it was just f at P2 minus f at T1 is what I was thinking. But that seems too simplistic. That seems way too simplistic. So they didn't give me the functions, did they?
Write an integral in x for dA.
No. But you can. Also don't see an F. Right? So is it going to have to be U at T2? Oh, that has my screen first. It was already there by them. Yeah, maybe I. Correct. Wow, that's what they wanted. That just seemed too simplistic. It was. Does it tell you? No. In my coding, I can tell what level they are. But. Okay. I thought I was looking for something more intricate. You know, like them giving you an actual function for you that you needed to do. That just seemed too simplistic, quite frankly, but okay. Yeah. Alright. So a particle moves along the x-axis as shown in the figure. When is the particle moving in the x minus direction? So that's asked me when my slope is negative. I would say from 3 until 5 something. So I guess I'm going to have to pick t greater than. Good. All right. Part B. Oh, you wanted part C, right? I was thinking I had to do all the parts to get up to it. Let's see what C is. The position of a particle at point in time is given by this, where x is in meters and t is in seconds. What is the velocity of particles in meters per second? Ooh, that's a good one. It's easier than you think. Let me grab one resource, okay?
Wait a second. T is 0.
Ah, I didn't mean to do that.
I do. I'm trying to use like an expression. Yeah. So you just get the
So you need this equation, you need your equation sheet for the fact that you want to grab these calculus functions here. Okay? So what we're going to do, is we need to we want to find, there's the position, we want to find the velocity, so we need to do the derivative of it. So let me grab that position equation so I can be lazy and not rewrite it. Alright, and then from here, from my equation sheet, I'm looking for the derivative of something that has e to the x, and that would be right here. I'm waiting for it to catch up with me. Yes, Mr. Cochran, I guess, needs a new computer. Some RAM or something.
So, there isn't an A in this problem, is there? What is it?
That's where I need to move this. Come on. So the derivative of just this exponent is negative 2 t to the minus 3 dt. Because I've got to bring the t down front, lower that by 1, and then I also have to do the derivative of the inside here, which is what gives me the dt. Because the derivative of t minus 3 is dt. Because it's like if this was negative x squared, right? I get the derivative of that would be negative 2x, and then the dx is actually the derivative of x. So here, and I see how I kept the x. Here, I kept the t3 because it's like the x. It just happens that the derivative of the variable, which is t minus 3, is dt. It's chance. If it was like 2t minus 3, the derivative would be 2 dt. You want me to show that? It's a seldom remembered thing, except when your calculus teacher asks you that you're taking the derivative of this variable, not just slapping a dx on it. Okay? So, our v to the t, as they're putting it now, is going to be negative 2 t minus 3 e to the negative t minus 3 where dt. Yeah. Yep. That should be it. And then substitute in. I'm listening. We're going through the answer. So the elapsed time, you got that too from the number of frames, right?
Yeah.
Okay, good. So constant acceleration. So nicely they're telling us, hey, use your algebraic relationships, and so we're going to be able to use what is it? And it started from rest, traveled 76 meters. So it's really up to you which one you're more comfortable with, because you have time, you have displacement, and you know that those are right? So you could go, d equals d naught plus v initial delta t plus 1/2 a delta t squared, and 0, 0, you have t, you have d, find a. And then that's the fourth one, and I could do that because it says constant acceleration, so I know it's the algebraic relationship. Move with this acceleration, 1 speed, it'll reach after 7. So then saying, hey, remember that v final equals v initial plus a delta t, and v initial is 0. And then what would its altitude be? It's saying go back and use this one. Yeah. Cool.